So this was the first part that is related to instruction processing and how the architecture defines these things. This is less relevant to us in the operating systems course. It's much more relevant to other people. Um, the only relevant part of it is that knowing that the size of one instruction in the ISA would be basically defined by how many addresses it takes as input. And that brings us to the next element of ISA that actually has quite significant effect on the way we design operating systems. And that is basically its memory organization. The memory organization of an ISA defines mostly two things. The first one is the address space, which is basically how large the memory that the machine can handle, how many uniquely identifiable locations in memory that you can handle, and that's basically your 64-bit processor versus your 32-bit processor partially. That is defined by how many bits you have for addressing locations in memory, but not just that. Okay. There is also the addressability, which is basically how much data does each uniquely identifiable location store. So if you go to memory, how much data is present in each location that you have just defined in the address space. So you can have byte addressable, which is most instruction set architectures. So if you go to a location, you just find 8 bits, and that's byte addressable. But there are, for some supercomputers, you have 64-bit addressable spaces. That basically means that you, when you fetch from memory, you will fetch the minimum number of bits that you can fetch at any point in time is 64 bits, and that's 4 times what you would fetch in a byte addressable machine from, I mean, as a minimum, because a byte addressable machine doesn't mean that when fetching data from memory you will get 8 bits, because you can read one memory location, two memory locations, three memory locations, four memory locations at the same time, depending on how the instruction set architecture is, what it allows you to, but depending also on the width of the instruction set architecture. So most architectures would actually bring 4 bytes at a time today, and that's 32 bits basically. So you can bring, in byte addressable, you typically bring 4 bytes at a time. And then it also defines your support for virtual memory, which we kind of touched upon in the first lecture, the second lecture of the course, but we have not really talked about in more details. And these actually make a difference when we start talking about caching pages and how what you do when you basically have cache misses and these things as an operating system, basically from an operating system's context, because this is studied both from an operating system point of view but also from an architecture point of view, because it has two aspects. Then that, I mean, I keep saying the word registers, and a register is basically a special memory place. And part of what you define in the architecture is how many registers do you have. So how many specialized memory places do you have? The size of each of these registers, is it 32-bit? Is it 64-bit? Is it 8-bit? Is it 4-bit? Because these were all sizes of registers. And this is part of what defines your 32-bit architecture versus your 64-bit architecture, which is basically how large is your special register. And registers in general can be both general purpose registers, so the architecture might basically have programmable registers which can be used for different things. They are still special memory, but they are more general purpose. They are not basically assigned to a certain task. But you can have also very specialized registers, which are basically things such as the program counter that I keep talking about. It's basically a special purpose register, so it's a 32-bit or 64-bit register in your architecture that basically defines how, or I mean, how do you call instructions in your memory, basically. And why is having registers a good idea? Sometimes it's because you have some special purpose stuff that you need to run, like the program counter. But the other point is that you might have some data that you actively use. So you might be there might be like these 64 bits in your memory that you keep actively reusing, and then basically going to memory to fetch them versus just having them stored in a register makes a huge difference and has a huge performance cost. So you have some of these registers to basically keep the data locality, yeah, to try to keep your your data close to the processor, close to where it's actually processed, and not having to communicate with the network. Sorry, with the memory a lot. And there's this is one thing, and there's also something that's called temporal locality, which basically says that okay, if you are accessing memory line number 10, you're probably going to access memory line number 11 next. And then it makes sense, since calling memory, getting stuff from it takes quite a bit of time compared to how fast the processor is. So it makes sense to basically try to get memories and the memory in chunks instead of just getting it in like line by line or word by word. It's basically you don't go fetch from memory, then come back, then go fetch from memory, then come back, but you rather go fetch a block and keep it near you. And storing these values in registers. So if you're accessing 10 now, then you're probably going to access 11 and 12, and just fetching 11 and 12 while 10 is there is some operation on 10 makes sense, because then you have the 11th and the 12th memory line when you need them. Again, what's a register? I mean, you have the memory, which is basically an array of storage locations. It's well, it's some 64-bit, 8-bit, 64, 32-bit lines that look like that, and you address them basically using an index. And that index is your program counter typically. But you have on the side registers which are given special names. They are instruction. They are related to your instruction set architecture, and they do not have addresses. So you do not call the PC the program counter by calling M2, but rather you go for the PC. And you have general versus special purpose registers. So these registers, when you start talking about them, yes, you can actually have, you can try to implement a system where you just have one single special register, or not even that. You can have it like the first 50 lines in memory or something, that these are your registers. But this entails that you will need to communicate between the ALU, your main processor, and going to memory every time you need to basically change the program counter or something, which will have a huge performance cost on your system.